Hi everyone, welcome to this introduction to, or maybe for some of you, a review of pertCharts. pertCharts are great in project management because they allow you to map out all of the tasks which need to be completed in order to finish a project. You can map the tasks out in sequence, and you can also identify how long it will take each task to complete. So here is an example of a PERT chart. We can see that some of the tasks cannot start until another task has finished. For example, this task here cannot start until this task has finished. Okay, we can also see that some tasks can run in parallel with each other. So we've got a series of tasks here which are running at the same time as this series of tasks and this series of tasks. So things are happening in parallel here. So this is another great feature of pertCharts. It allows you to see the dependencies of tasks. Now, to help us understand how to draw a PERT chart, we're going to use a past paper question from Cambridge International Examinations 9608 syllabus paper 4, and this is the question. A software company is developing a new application. The project manager has created a work breakdown structure as shown in the following table. So basically, the project manager has just listed all of the tasks that need to be completed in order to finish the project. The project manager has also kind of guesstimated how many tasks it will take to complete how many days it will take to complete each task. And interestingly, the project manager has indicated the predecessor of each of the tasks. So task B is going to last for 8 days, and its predecessor is task A. And we can see that here on the PERT chart. Task B is going to last for 8 days, and its predecessor is task A. So using this information, we're going to complete the following PERT chart. Okay? Now, the way that I like to start this is to identify things that I can fill out quite quickly. And if we look at the end of the project here, this is obviously when we're rolling out the application. Everything's finished, the coding, the testing, the documentation. It's done. We're rolling out the application now. So I'm just going to assume that this task here is task I, which lasts for 3 days. I'm also told that the predecessor to task I is task H, which is this testing the application and integrating it onto the server. So task H is the predecessor to task I. So this must be task H, which lasts for 5 days. Now things get a little bit tricky because we've got all of this kind of parallel tasks here. Let's have a look back in the breakdown. Let's go to task C. Task C's predecessor is task B. Okay, so there's task B. This line, or this line, or this line is task B. Task C. Oh, look, task D also has a predecessor of task B. So one of these lines is C, and one of these lines is D. Hey, check it out! Another task. Task E has a predecessor of B. So one of these lines is C, one is D, and one is E. The question is, which one is which? Well, let's see if we can find any clues. Task C is to develop the server code. Oh, task F is to test the server code. So here we've got a kind of dependency. We can't test the server code until we've developed the server code, right? So they can't run in parallel. No. They do it one after the other. So I'm going to gamble that this task here is task C, develop the server code, and this task here is task F, test the server code. So that's what I'm going to do with those. develop the server code, test the server code. Now let's look at another one that had a dependency of B. Develop the application code. Okay, which one? Is it this line or is it this line? Are there any clues? Develop the application code. Test the application. First we develop the code for the application and then we test the application. So D and then G. I bet you D and then G. So let's put in develop the application code, test the application. So that leaves us with this one, which is going to be E, because it's the last task that has a predecessor of B, and E is user interface development. That kind of makes sense, right? We can develop the server code, we can at the same time develop the application code, and while all of that's happening, we can also design the user interface. So all of these things can happen at the same time. So that is the completed PERT chart. Now let's move on to question B. Calculate the critical path and state the activities on the path and the duration of the critical path. Now if an activity is on the critical path, what that means is if that activity is delayed, the whole project is going to be delayed. Okay? So, for example, if we were to delay task H, if that was 7 weeks instead of 5 weeks, well, task I can't start until this is finished. So we have just delayed the whole project by 2 weeks. So for sure, task H is on the critical path. So let's see if we can figure out all of the tasks that are on the critical path. So we'll start with task A. For sure it's on the critical path. If we delay task A, then task B will be delayed, and actually the whole project will be delayed. So task A is on the critical path. Task B is also on the critical path. If we delay task B, everything else is going to be delayed. So those are on the critical path. Now let's have a look at these 3 parallel scenarios. Tasks C and F take 6 weeks to complete. That's the minimum amount of time required to complete those tasks. We need 6 weeks, no doubt. Tasks D and G require 7 weeks to complete. We need 7 weeks. So that's cool. C and F can be delayed by a week because they only need 6 weeks to reach point 6. This node here, 6 weeks to get there. D and G need 7 weeks to get there. That's fine. We've got 7 weeks. That's fine. So C and F can be delayed by a week. Does that make sense? Now let's follow this path here. E all the way through to this node, 6. E and G take 8 weeks to complete. We need those 8 weeks. We can't make that any shorter. So the critical path at the moment is A to B to E to G. Okay? We need those 8 weeks. We can't make it 6 weeks or less. Okay? We can delay C and F because they only need 6 weeks to reach point 6. While that's happening, E and G take 8 weeks. Does that make sense? So we have an extra 2 weeks if we need them to do C and F. D and G need 7 weeks. But E and G, because we need 8 weeks to complete all of those tasks, we've got 1 extra week spare to complete D and G. We need those 8 weeks to complete E and G. Okay? So the critical path at the moment is A, B, E, G, and then we just continue H and I. No choice. We know that if we delay H, we're going to delay the project. If we delay I, we're going to delay the project. If we delay C by a week, that would be 5 and 2. That's 7. We've delayed C, but no problem. Because E and G require 8 weeks. So we can delay C if we want, or we can delay F, we can delay D by a week. It wouldn't impact the project. Okay? Okay, so the activities that form the critical path are A, B, E, G, H, I, and the duration of the critical path is 6 plus 8 plus 6 plus 2 plus 5 plus 3, 30. For activity F, state the earliest start time. Well, there's activity F, which starts at node 4. How long does it take to get to node 4? 6 days, sorry, I'm saying weeks, aren't I? Sorry, days. 6 days plus 8 is 14 plus 4. That's 18 days to get to that node. So F will start on the next day. The earliest start time for F is 19 days into the project. The latest finish time for F, well, the latest finish time for F is here. And do you remember what I was just telling you about the critical path? Just follow the critical path to find the latest finish time. 6 plus 8 plus 6 plus 2, which is 22. 22 days to get to point 6. That's the longest time available. And point F, which finishes at point 6, has that time. It's got 22 days into the project to finish task F. And that's an introduction to PERT charts.